number A, and this is the ESNet session. So it'll be me, and then Eli, and then me. And we've called it the ESNet sandwich. Eli, we've decided, is a black bean patty, so it's a really nice, healthy middle. It's gonna really be nourishing, nutritious, and then I'm just the pieces of bread that you can probably just take off if you're on a low-carb diet. This slide, I really want to acknowledge these people, but they are not for this presentation. This slide got in here by mistake. So actually, Dale always helps on all my presentations, but all the other ones were that was for a different presentation, so I apologize for that slide being there. But they were really helpful on this other presentation that you're not going to see. So I want to start off with a problem statement. This is something we've all seen before. The internet was not designed for security. It was not designed with security in mind. We hear that all the time. So this is my little problem statement about that. I call it asecure. It's not really insecure, but it's just a lack of security or lack of security awareness. And that's sort of considered the fundamental problem of the internet. So to illustrate some of that stuff, and particularly how that asecurity has to deal with the naming infrastructure and the routing infrastructure of the internet, I'm going to tell a story that I think is a pretty good example. So about 11 months ago, someone, we don't really know who, started announcing the prefixes you see on the screen to an ISP, and those routes got propagated to a good portion of the global internet. Those particular prefixes are interesting in that they are the prefixes that are used by the AWS, Amazon Web Services, their Route 53 DNS service. And because of the way these prefixes were announced at the time, these prefixes, if you look at your route views or one of your internet, if you look at your own router, you'll see that these are all now announced by AWS as /24s, but some of them were announced as /22s or 23s. So these /24s took precedence in those, among those providers that accepted these particular prefixes. And the fact of the matter was that it happened to be the set of prefixes that controlled AWS's Route 53 DNS infrastructure. Why is that interesting? Well, somebody took those prefixes, routed them to a server that was at an internet exchange point, and then took one of the domains that served on those servers and decided to redirect traffic to it to a different site. So when you resolved it in DNS, it went to the wrong, bad IP address. It looked like the right IP address, but it was the wrong one. And it happened to belong to the Ethereum currency exchange. Ethereum is a cryptocurrency, and my Ether wallet is a wallet, or basically a little mini bank that holds, that allows people to keep the currency in that particular, it's sort of in an account right there. It's a wallet, basically. It's a virtual wallet. The malicious servers, so this is sort of a three-level attack. First, you inject something bad into the routing infrastructure. Then you let that point to a bad DNS server, which then in turn points you to a bad website, which then collects your credentials or just steals your money while you're logged in. So there's some interesting parts about this. This site had a self-signed HTTPS certificate. So there were warnings. Some people clicked through those warnings. In some cases, though, because they already had cached cookies, they were able to, in some cases, continue sessions. Some people say they never got a warning. So they may have been able to continue sessions using the cached cookie credentials. And at any rate, they got enough people to bite on this that they made $150,000 in the Ethereum cryptocurrency, which then they probably went and sold it, and then it went down to like, $28,000 or something like that, because that's how cryptocurrencies work. So this is kind of an interesting thing. Why do these guys do this three-level attack? Okay, so it lends itself to an interesting question, and I'm going to steal some slides from Chioma, who gave this at Nanog just a few weeks ago. Why do you hijack the DNS instead of just hijacking the website? He has some theories. Maybe they were drunk, which I think they probably weren't. They probably got drunk afterward, so they had 150 grand to spend on booze. But Choma thinks one of the reasons is perhaps that DNS servers, you can redirect a site just pinpoint, granular, if you have a DNS server and they don't get as much traffic as the actual website. So if you try to redirect Amazon's entire cloud infrastructure, you end up with having to handle all the traffic of their sites. It's going to be a lot more visible if you're actually trying to hijack that. It's also kind of hard in the cloud to hijack a particular site because it might bounce around, it might move around to a different resource, it might change IP addresses. Cloud's supposed to be resilient, right? So in this particular case, if you grab all the DNS servers, you've got a choke point where you can then try to redirect maliciously redirect traffic to this particular site. So he thinks it's more cost effective. There's another reason I think a little later on I'll talk about, but it does make DNS a likely target for BGP hijack attacks. So think about what we're talking about. We've got like 2 points of failure here, basically. We've got the routing system and the naming system, what I just talked about here. Now, we talk about how this had a self-signed certificate. And you must have had to click through some warning. Maybe you didn't. Maybe there were ways of continuing sessions without the warning. But if we just fix TLS a little bit more, remember, we're on version 6 now of TLS. It says 1.3, but it's the 6th iteration of SSL TLS since we started this. I'm going to talk a little bit later on about how I think security protocols are hard. So that's a little bit of a preview there. But the truth is, shouldn't this be fixed? Can't we just tweak TLS? Why can't we just make these warnings bigger or make people not able to click through them or not able to click through them as easily or have to pay money to click through them or do something else? And then it turns out, well, if you can hijack the BGP and you can hijack the DNS, or if you can hijack the BGP or you can hijack the DNS, you can grab your own certificates all you want. In fact, there were recently some DNS hijacks over the winter break where they did hijack DNS and then went out and grabbed a whole bunch, the bad guys went out and grabbed a whole bunch of certificates. And so it turns out you can do this. I happen to say BGP, but in fact, you could do it with just plain old DNS hijacking as well. So the idea that we can make HTTPS better, we can make TLS better, those are all good things, and we should make them better. But that's not necessarily enough if the DNS infrastructure and the BGP infrastructure remain vulnerable. In other words, to be really dorky and borrow from Dune, whoever controls the DNS and BGP pretty much controls the whole damn internet. So what do we do about it? What technology is there out there to help us with it? And just to illustrate, I did want to steal a slide from the Internet Society. This is just how many BGP attacks there are. Most of these are probably just misconfigurations, but some of them, as we know, are malicious. So one of the obvious things we can do is we can take a digital certificate, which relies on digital signature technology, and use that kind of technology to make an assertion about what autonomous system is allowed to announce what kind of route. And we can make sure that the routing system is populated with routes that are the correct length, so you're not advertising longer prefixes, and have the correct origin. That means the AS number, the autonomous system, is what we expect it to be. We can do that and validate it, and we can use a chain of trust that points to a set of certificate authorities. Today, the set of certificate authorities happens to be coterminous with the regional internet registries, which is both good and bad in certain ways. So essentially, when you do these route origin attestations, or ROAs is what they're called, you can basically specify who's allowed to announce your route. Hopefully it's you. And you can specify what length that route, how that route should look in the internet. So this is great, okay? And there's lots of other better news about it. First of all, it's really easy to set up. You use a computer offline, well, it's online, but it's not inline. And that computer does all the hard work, does all the cryptographic validation, and then it talks to your router and it says, this route's good, this route's bad, this route I don't know about. Very simple. And then you can use your own policies in your router to decide whether or not you drop the prefix or you just depreference it or whatever you want. So it's very flexible in what it allows you to do. And in this particular attack, if ISPs and everyone in the network had used this particular method and they had dropped the invalid prefixes, it would have thwarted this particular attack. Would not have happened. Everyone was doing this. Now that sounds great, okay? There are a couple problems. One problem is that computer that you sit next to your router that does all the work, the software that makes it do all that work hasn't really existed until recently. So there was some very nice, some very good software that was written by Rob Austin and Randy Bush, this Dragon Research Labs and RPKI.net. And it was really nice. I mean, it was set and forget it. It would work. But they were funded by DHS. That grant ran out. It's not really maintained that much anymore. RIPE, the European RIPE NCC and the European Research Lab, they have an RPKI validator, which runs on Java. I have never gotten this one to work, maybe just because I don't want to work my way through the configuration file, maybe because I don't feel like installing all the dependencies. And part of the other reason I've never gotten it to work is because there's actually some better stuff happening now. So luckily, this particular situation is improving. NL Labs, which is the Netherlands kind of research arm of their registry, they have something which they cleverly call RouteNator 3000, and it's written in Rust. And it's actually really cool. It works really, really well. Rust, if you don't know, is a compiled language. So although it's high-level language, you compile it and you have a binary to run when you're done. So I actually was able to set this up. You know, they made packages for this RouteNator 3000. I was able to set that up faster than I was able to set up the RIPE Java-based RPKI validator. And that's just, part of that's just me, part of that's just because I didn't like the configuration file. There was other stuff. There are other implementations coming along. Cloudflare has an implementation that's written in Go. That's also a high-level compiled language. And OpenBSD is doing one, and one of the driving forces behind that, and if you know him, you know he's always a driving force, is Job Snyder's. And he's working on this one called RPKI Client, and that's written in C, also a compiled language, mid-level compiled language, if you will. So there's a lot of good software coming along that's doing this validation. So that's helping us a lot. But there's still another problem. This is the ugly problem. In the North American region, because the certificate authority that we have is our regional internet registry, the American Registry for Internet Numbers, or ARIN, they have a set of legal agreements that they want you to sign in order to generate your own ROAs. And these legal agreements include the Registration Services Agreement, which is sort of the main agreement you have to sign with ARIN, plus a separate agreement, which includes all sorts of wonderful legal language like indemnify, hold harmless, and defend. ARIN, if somebody else sues ARIN on the basis of your use of their service. Now think about what happens. If ARIN screws up, you block somebody, or you block people from getting to a particular site, and it's just your clients, just your users, but because you've blocked them, that site loses revenue. They could come back and sue ARIN, but they're really suing you because you signed this agreement that indemnifies them against everything. Moreover, ARIN actually gets to decide whether you settle or not. Gets to decide how the case is prosecuted, even though you're paying for the lawyers and you're doing all the work to defend ARIN. That's a pretty strong indemnification clause. Most legal experts that I've talked to said that's a pretty strong indemnification clause. And for a lot of people, including state universities, it's a toxic one. They can't sign that agreement with that clause. So this caused people to hurry up and copy down this URL because I'm going to take a blurry picture of it because I'm going to, oh, too late. This has actually caused folks, the slides are going to be made available, so don't worry. If you want, and if they're not on the website or whatever, just ask me. So it caused this paper to get written, and it was, I believe, funded by the NSF. There was an NSF grant to help do it. And it was two professors, a professor and a grad student at UPenn, and the professor is both a professor of law and computer science. So he deals a lot with information law. And so they decided to figure out, okay, how can we fix some of these problems? Can we make recommendations to Aaron? And these are the recommendations that they made. So part of it is, change this to an as is, no warranty, rather than this indemnification clause. Do things like just simplify the relying party agreement. It turns out that you not only have to sign an agreement with Aaron that includes indemnification if you're going to generate your own rows, but if you're going to run one of those validating caches and you want to validate Aaron routes, you have to sign an agreement with them also that includes an indemnification clause. So there's like sort of, they get you going both ways here. And then one of the things I like too, in particular, is that fourth bullet, because it was my idea, which is create a separate CA. Now, it doesn't have to be completely separate from Aaron, but one that is a separate business entity from Aaron so that it runs just this thing. It could be closely affiliated with Aaron in order to have Aaron, because Aaron still has to be able to certify that you are assigned the legitimate assignee of the resources for which you're generating ROAs. But because you have this separate entity, if it gets sued, they can't come after Aaron. So really you create like a separate LLC or a separate 501c3 to do this kind of stuff. Now, the community can also do this. We can come together as a community in R&E, and we can say we want our own CA. We can come together in, like, for example, the NOGs, like NANOG, and some of those groups could come together. We could take the R&E and the NANOG community, bring them both together and say, we're going to do our own CA. But we have to have that information exchange with Aaron to make sure that we can validate the resources. So there's still a role for Aaron to play here. So the real question is, how do we do this in such a way that reduces the exposure to legal liability but still works? And we haven't quite ironed out those issues yet. But because this paper was published and because it was done in cooperation with Aaron, this was not like a adversarial thing. It was done in cooperation with Aaron. It was done in cooperation with a lot of us. That actually indicates that we may actually get some traction on some of these things soon. I was hoping I'd be able to have some news by now, but maybe in the next few months, we're going to see some changes to the way Aaron does this stuff. But right now, it's a little bit difficult because of the way you have to deal with agreements in order just to use this technology. Okay, I go back to my good slide because I want to say, hey, look, all the good stuff about RPKI would have prevented this MyEtherWallet attack, but it actually turns out DNSSEC would have also. So let's talk about that for just a second. I'm supposed to be talking about origin validation, but DNSSEC actually does something very similar to RPKI. It is a digital signature attestation which is combined with a chain of trust, which basically says the names and IP addresses in my DNS were curated by me, and that is where I intend for you to go to get to my resources. So it is a way for you to validate that when there's something in my DNS, it's something I put there. Now, of course, it's not perfect, but it is something you can do right now. You don't have to sign an agreement to make this happen. So it turns out that if MyEtherWallet had used DNSSEC, just like if they had signed if they had ROAs for their routes, they had used DNSSEC, signed their zones, and everyone validated. That's sort of the important provisos. Everyone else validated those DNSSEC records, just like you need people to validate RPKI routes. Then this would not have happened. The MyEtherWallet attack wouldn't have happened. Except that AWS Route 53 doesn't support DNSSEC, so that's kind of a non-starter. The only way around this is either to not use AWS Route 53 or tell AWS Route 53 it's time to support DNSSEC. You just had a customer that lost $150,000 in part because this is a technology that you don't support. So I don't think they're liable or anything, but I'm not a lawyer, so I don't know. But I just want to say that this is something that they should support. This is something customers probably want. And I would also say that DNS services that don't support DNSSEC or don't use DNSSEC will continue to be vulnerable to these sorts of things. So it's important that we deploy this, and it's important that we move forward with getting our service providers to use it and everyone else to use it. So in a way, DNSSEC actually is a form of origin validation. Now, I think a lot of us have talked about DNSSEC signing before and what it's like, and yeah, it's kind of hard. There are new failure modes that it introduces. It's actually getting much, much easier to do signing. A lot of the main open source software already supports automated signing and re-signing of zones. But you don't even need to worry about that right now, I would say. I'm going to say something a little bit different than you might hear me say. You might always hear me say, always use strong cryptographic protocols, always sign everything, always use digital signatures whenever you can. But it turns out you may not need to sign your zone. But what would be nice is if you turned on validation, because that means that for those zones that consider their resources important enough that they're going to sign their DNS, your users can then validate or take advantage of your validation to make sure those signatures are correct. So if it's my Ether wallet today, maybe it's a major bank tomorrow. And if they are concerned enough about their resources and about their customers' access to their resources, then they may start signing their zone. You should be able to validate that zone. If you take the example of TLS, the early days of HTTPS, the HTTP protocol with TLS, or with SSL as it was originally called, very few people went out and got those certificates and put a port 443 HTTPS website up, unless they actually had people doing e-commerce type stuff. Remember when we called it e-commerce? Like that was different than regular commerce? Now it's like just commerce. So at the time, though, very few people were doing this. A very small percentage of sites actually had certificates. But everybody had a browser that was capable of validating those certificates. Because all of the people who were trying to make e-commerce work knew that you can't have a situation in which there's not 100% of the capability to use the signing, the validation and encryption technology. If you didn't have 100% coverage, then you have a whole group of people that can't use your services. So they knew that you had to do, if Netscape wanted to sell web servers that could do this kind of stuff, that could do HTTPS, they had to give away browsers that could do the client side of HTTPS. So you didn't need 100% coverage on the server side, but you needed 100% coverage on the client side. That's what I'm arguing here. And the other reason I'm arguing that is because it's really easy to do. First of all, if you use any of these services, you're already doing it. If you're forwarding your DNS server, your recursive DNS server, to any of the services here, they are validating for you. On the other hand, if you want to do it in your own web DNS server, here's the options of a bind DNS server. There's a huge amount of stuff you have to add. I'm gonna have to make the font much smaller to show you what you have to add here, so get ready. Get your cameras ready. You can take a blurry picture of it. All done. Now, obviously, you want to do like best practice QA, change management, all that stuff. You're going to do this on your production recursors for your campus. But this is something you can do at home right now. This is something you can do in a test bed network right now. And by the way, there are other types of DNS servers out there. They're similarly easy to set up, but most of them in the next versions or in upcoming versions, they're going to have this turned on by default. You will have to do something extra to turn it off. Now, in the early days of DNSSEC validation, like when I turned it on 10 years ago at UC Berkeley, it was, you would run into problems where someone would screw up their signing. Nowadays, if you screw up your signing, no one from Google can get to you. So you better fix it fast. No one from Comcast can get to you. So you better fix it fast. So we're no longer in this state where you're using some new technology, somebody else screws up and they blame you because you're using the new technology. Now we have a situation where because all the big guys are using it, we can sort of hide behind them as a screen. There's actually some pretty cool, this is sort of the public, this is not so much public shaming, this is public praising here. There is a site, see the URL at the bottom there, APNIC, this is mainly Jeff Houston who does this. This is really interesting. It talks about how DNSSEC validation can work across regions, across the world. He basically measures DNSSEC validation by using carefully placed ads with URLs in Google. So in the Google AdWords, anything that has a Google ad, he has these stuff with URLs, some of which can be resolved with DNSSEC and some of which are intentionally invalid. So if you're validating DNSSEC, you're going to find that some of these URLs don't work. He's able to measure that, whether you contact the URL or not, and then decide who's validating, who's not. So right now, and when I say right now, these numbers shift a lot. So there's a lot of statistical noise in here. So don't take them too seriously. But if you're over 90% or over 95%, you're doing really well. You know, Santa Cruz right now is leading the league. And then Stanford, LBL. I wanted to kind of do like cross-state rivals for a while, or cross-town rivals. So Stanford right now is beating Berkeley. Right now. What I'm thinking I'm going to do is actually take because these numbers are so good and you get all this data. I want to take both the men's and women's NCAA brackets for basketball, and I want to fill out the whole bracket, the Final Four and the whole thing based on who's doing better DNSSEC validation. That'd be a fun thing. I talked about making TLS better as a possibility as well. And there are ways of doing that. One way is sometimes called certificate pinning. Certificate pinning, the way it was originally implemented is you hard code in a browser, like certain major websites can only use certain certificate authorities. So if I try to go get a certificate from Komodo and it turns out I want it to be google.com, and it turns out Google only gets certificates from GoDaddy, you can code that in as this is the correct certificate authority for Google. And that will actually prevent people from validating the incorrect Google certificate. So I would say that doesn't scale. So one of the ways you can do this using DNSSEC is there are basically two things. One works on the client side and the other works on the server side. DANE is a mechanism of asserting this is the correct CA for me in DNS using DNSSEC signatures to validate that. And then you can say, okay, I can do the regular TLS validation, or I can put the certificate fingerprint directly in the DNS and sign that as well. So this gives you more ways to validate their certificate, or ways to more carefully validate the certificate. It also allows for scalable pinning. There's something else called CAA, which is to tell the certificate authority, hey, if you're not this certificate authority, don't issue a certificate for this domain. So if I call up Komodo and I say, hey, I'm Google, give me a certificate, they can look up the record in the DNS, the CAA record, and they can say, oh no, only GoDaddy is allowed to issue certificates to Google. So we're not going to give you one. I'm not going to talk about manners. These slides are in there for your reference, so I'm going to skip them. But what manners allows you to do is it's a set of best practices for ISPs and service providers, but you can also do some of them on enterprise campuses as well. And I also tell you a little bit about what ESNet does. But for the most part, what these things are is they're sets of best practices that both help limit the impact of route hijacks and also limit the impact of IP spoofing, which is also a problem in terms of internet security. So manners is a good way of getting to that point. I don't have the URL for this, but look up IRR Explorer in your Google or whatever search engine you use. This is a really cool way of looking at your routes and seeing if they are correctly documented in either RPKI, if you're using RPKI. If you're not, it'll also tell you, are they supposed to look, am I seeing this in BGP and in WHOIS and in the IRR system, the Internet Routing Registry system? Does this all look good? Like, for example, with UC Berkeley's 128.32/16, looks good. There are other networks where, well, that doesn't quite match what's being announced. What's being announced doesn't quite match. This is an ESNet route. What's being announced doesn't quite match what's in the ARIN registry, but it matches what's in the IRR, so that's actually okay. You could actually take the ARIN WHOIS, and you can add information about the origin AS. You can do this right now. You don't need to sign an agreement for doing it. You can put this in your WHOIS. So in addition to, I mean, RPKI is obviously a lot stronger than this because it has digital signature. But at least here, you can put this in ARIN WHOIS, and it's another point of reference to say, yes, this is the correct AS number for this prefix. And I'm going to conclude. A lot of people ask, what about BGPSEC? Can I validate the entire path? And BGPSEC is brand new, and there's not a lot of support for it. But there's also some question about whether we've implemented it correctly. And I'm not going to say much about this because the people who wrote the BGPSEC spec did a very good job, and they're very smart, but they may have made some things, done some things that might need a little tweaking. So we may not be ready for BGPSEC yet. The jury is still out on that. Let me just go back to my problem statement. And here we are again. And if you think about how we've tried to secure the naming system and the routing system, it kind of turns into a problem of, well, yeah, let's do RPKI. Oh, but it's hard and there's legal issues. Let's secure the naming system. It's insecure. Well, it's hard and sometimes things break. Sometimes we end up getting caught in this trap about, like, we need to do something about internet security. But the truth of the matter is, sometimes the things we try, sometimes the controls we apply end up being riskier, or at least have higher costs than the expected value of just accepting the risk. So we do have to think about this when we talk about the internet's insecure. We really have to think about, is the cure worse than, is the cure worse than the disease? And so I'll just leave it with that and take any questions. I'll go back to this slide so you can read the conclusions. These are the substantive conclusions. And my answer to that question is, in the case of routing security and DNS, no. The cure is not worse than the disease. But I don't know. Eli.
So
and also use NOD rules, so Eli Dart of ESNet.
Hi, that's live. Eli Dart from ESNet. So you sort of hinted around the edges at some of this, more for DNSSEC than on the routing side. How amenable to incremental deployment is this? Right, because I mean, so for example, when we were all working on IPv6 to begin with, right, it was like, okay, you get routing up and then you get a service running, using IPv6, and you can roll around with that and try and understand it a little bit before you go and go whole hog, right? Stuff that has like a large blast radius. So how much of this can we do incrementally, where we can sort of take the minimum viable first step and learn about it?
Right, so the cool thing about RPKI is it lets you import that database into your router without doing anything. So you can actually have data about what routes are valid and what routes are not valid, and you can decide what actions to take. You can actually import that information into a route policy that says, I want to local pref this a little bit higher or a little bit lower, but I don't want to drop it. So that you can then look at that, or you can actually do something like tag a community with it. So you can say, I'm not going to do anything with this prefix, but I'm going to put a community on it that's going to let my customers or my downstreams, or just let me know that this route is either valid or invalid or unknown. So there's a tremendous amount of flexibility you can do with RPKI as kind of an incremental deployment. You don't have to turn it on and say, I'm going to drop prefixes right away. The flip side of that, though, is if you do it that way, you're not going to protect against the MyEtherWallet problem because they were announcing longer prefixes. So in that particular case, they're always going to be preferred unless you actually drop prefixes. Does that make sense?
Yeah.
I just want to let folks know we're into our break. So if you want to continue to ask questions, welcome to do so. Otherwise, our next session starts in about 5 minutes.
I didn't realize we had a designated break. I thought we just had Q&A time. Steve.
Steve Huter, nsrc.org. Michael, given the complexities you started with on, RPKI implementation and the dynamics of dealing with RIRs and some of the legal, implications, concerns, I guess, from your experience in this community, do you feel like we were on the right path to forge ahead and push for RPKI implementation, globally, or do you see another scenario that might be better? Could this be done in a TLS-like way as an alternative?
So I don't think it can be done in a TLS-like way, although, and the reason for that is just the vulnerability of certificates. If I can hijack your prefixes, then I can find a way to get a certificate in your name, basically. Same thing with your DNS. That said, I think strengthening TLS and using other mechanisms to validate TLS certificates, not just the current one of the CA cartel that's already pre-programmed in your browser or something else like that, I think that would be good. I think that helps. But yeah, RPKI, the thing about RPKI that's interesting is that it is sort of the foundation. So if we did want to move on to something else like path validation, BGPSEC, that sort of thing, we kind of need to start with RPKI. And so even if the BGPSEC as it currently stands, and there's some smart people out there who say it's not really easily deployable as it is now, those same people are still advocating for RPKI because they're saying, we need to get this infrastructure working, we need to get people using it, exercising the code, doing the validations, validating rows, signing rows, doing things like that. So I don't know if there's a way around it. And again, I think that's the conundrum.
Right.
It's like something's wrong with the internet. Not someone's wrong on the internet, but something's wrong with the internet. But we don't know how to fix it in a way that is seamless and totally easy to deploy. And that's where I think
scale.
Yeah, and scales. So I think it's really kind of where we come in. As R&E, we should still be kind of leaders in this area. We have the ability to do that. And I think we can help. But I don't think there's a way. I don't think there's not an easy way. Security's hard. Security protocols are hard. Getting them right is hard. Like I said, version 6 of TLS. So that's kind of where we stand now.
Thanks.
Anyone else? Kevin, you must have something to say.
I'll say something, sure. Kevin Thompson, NSF. So I'm going to make what I'm sure you'll say is an incorrect statement, but explain to me why this is incorrect. Why can't CENIC or some leadership entity in the community stand up an alternative CA and just get this thing rolling? Instead of waiting for Aaron to figure out how to do things the right way.
You are not incorrect at all. That is absolutely correct. CENIC could do it. There have been discussions. I know that there are people in larger communities who've been discussing possibly doing this. The issue, the only concern is that we need to make sure that the resources that are being signed are actually being signed by the correct people. Right now, the RIRs have that information. But the question is, if you say, Kevin, you say you're nsf.gov, and you have a set of IP resources that have been assigned to you by Aaron, and you want me to be the CA and you want me to sign a ROA for you, how do I know that you really have those IP resources? And that's a question. If it's you, Kevin, and it's me, I know you and I know what resources you have. But that doesn't scale. And so that's really the issue.
So
How
it
do we
gets,
scale
it gets back to Aaron, but, you know, we don't have to scale to internet size, our community, right? That's part of our advantage, and I would argue allows us to maybe take that jump
Yeah.
without, you know, being, you know, stamped down saying, well, that's not going to scale. We can't do that. But
Right. Yeah.
fine, it won't scale in the big I internet. We're different.
Right. I agree with you, and I think that's actually a good idea. I do want to point back to you. If you look at this particular screen, you can see there's like the 4 different categories here. So the first one is what's actually announced in BGP. That's the origin AS. This is an ESNet route. Look at there's RADB and then there's RPKI. Now, we have not signed any agreement with Aaron that lets us do anything in their RPKI. So where's this coming from? There actually already is an alternate CA that's run by that RPKI.net. And so Job is taking that information and using it. So this actually happens. And the question is, can we make it happen as a community and can we scale it? I think that's an open question. I don't think I would not answer that in the negative, which is a stunning endorsement for me. One more?
Thank you very much. Yeah, let's go to the next thing.
Okay. Well, it's just Eli, so, you know.
All right, I'm going to be disruptive and swap in my laptop.
Do you want me to get your water?
Yeah, if you wouldn't mind, that'd be fantastic. Thank you.